I've been involved for quite a few years in building detectors, imaging detectors, and I had a £4.5 million grant to develop what are called active pixel sensors. And then from that we were awarded a £1.2 million grant to produce what we call a wafer-scale, which is as big as you can get, imager for medical purposes. I'm Nigel Allinson. I'm the Distinguished Professor of Image Engineering. What we developed was the world's largest radiation-hard imaging detector. It's radiation-hard, so it's not damaged by the X-rays which are used, say, in radiotherapy or for X-ray examination. This will spend most of its time doing things like chest X-rays, mammography, X-ray CT, etc., replacing the current technology, which is slower and gives poorer quality images. From this device, a spin-off company was formed called Isdi CMOS, and that has contracts to design devices like this for big medical instrumentation companies. And they will go into hospitals and replace the existing technology, which is called amorphous silicon, and will provide longer life, so it costs less, better quality images, and less dose to the patient, which is in fact most important, because every time you have an X-ray examination, you receive some radiation which is dangerous. From this work, which met one of the grand challenges of the Engineering and Physical Research Council, which had set the community to do, we then obtained further funding from the Wellcome Trust. Now we've started a project to look at proton therapy and instrumentation for that. So protons react very differently in the body to X-rays. With protons you can target an enormous amount of energy into a very small volume deep inside the body. And this will probably be the next way of doing radiotherapy. The government has agreed to 2 proton therapies to be built in this country. There are about 60 working in the world at the moment. So we will be building instruments using new types of detectors so that we can again do the quality assurance, we can measure the energy of the dose and the position, but perhaps most importantly, we'll be able to see in real time where the dose is absorbed on the tumour. And this will be, if you like, the Holy Grail for radiotherapists.